Welcome back to NE 630 nuclear reactor theory again. So we will start or continue the chapter before the last chapter, and this chapter studies the long-term reactor behavior. As we stated last time, we will study the fuel burnup. We will study the burnable poisons. We will study the poisons like xenon and samarium buildup in the reactor and so on. And those effects usually affect greatly the reactivity of the reactor on the long term. So let's start by studying the fission product buildup and decay. Fission products buildup and decay. So all of us knew that in thermal reactors, if you look at the yield for the fission yield versus the atomic mass number, you will get a curve like this for uranium-235. This is the thermal fission yields. So what does it mean, thermal fission yield? Can somebody tell me what's this? Explain what's this plot?
It's the distribution of daughters that you get out from the fission, like what particles it fissions into.
So if you have a uranium atom 235 as a target and you bombard it with a neutron as a projectile, it will split to two atoms, and it will give you on the average 2.45 neutrons as the number of neutrons from fission. So what this curve is, let's assume that we have 1 million fissile nuclei that we started with, and we have the fission for those 1 million nuclei. Then we start with a tweezer, nanoscale tweezer, picking up all the products, fission products from the reactor, from those million fissile atoms. So we will have boxes, and I will say, okay, there is one atom from barium, there is another atom from barium, here is one atom from krypton, here is another atom from krypton, and you start looking for the distribution. How many? You have boxes for everything from A equal to 1 up to A equal to, let's say, 200 or so. And you have 200 boxes. You start picking up with the tweezers the number of atoms that you got from the fission. Then, let's say you collected 10 atoms of barium, 15 atoms of this, 20 atoms of that, whatever. I'm just giving you an example. So if you divide the number of atoms by the 1 million, this will give you the fraction of those atoms that you get. Then if you plot this, you will get this shape here. And all what this shape is telling you, that this is the most probable outcome of the fission. So the most probable outcome of the fission will be krypton and barium. So Kr and Ba. So those are the two for the uranium-235. Of course, when the energy of the neutron will increase, you will go up something like this. Okay, and at this position, can somebody tell me what's this position? You have only 1 point, you don't have two. So anywhere here, you have 2 points. Anywhere in the curve, 2 points except this one, you have only 1 point, and this is usually the symmetric fission, A over 2. So you will split the nuclei, the initial nuclei, into 2 halves. So this is the symmetrical fission. And again, symmetrical fission is not favored with respect to the other asymmetric fission. So if you write the equation, it would be U238, 235 plus neutron and this will give you krypton plus barium plus 3 neutrons or so. And you have to figure out the, this is 92, this is 0. You have to figure out what's the atomic mass numbers. I think one is 146, I think, and the other one is 82, if I remember correctly. So, so this is just a review. So, if we'll assume that we will have N of T as the concentration of a particular fission product. So we will look for a particular fission product, and N of T is just concentration of fission product at time t. So what will be the differential equation that will give us the time rate of change of N of T? The N of T by the T will be equal to what?
Accumulation minus destruction.
So accumulation minus destruction, or production minus destruction, source minus losses. Okay, so what is the production? Production is coming from the fission. So you expect to have source term that's based on what? Sigma F phi, which is what? Fission. Yes, number of fissions. But each one of those fission will give you a curve. Yes, so if you are talking about, let's say, isotope here, let's say with AI, so the yield for this isotope will be something, gamma I. Yes, so I have to multiply by what? Gamma fission products. What's the yield? Where gamma fission product is just a fraction of fissions that produce the specific product of interest. How many fission will produce this product of interest? So gamma FP fraction of fission that produce isotope of interest. We will see what isotope of interest in subsequent lectures. So what's the destruction?
Minus
Lambda n A of t, or lambda n of t. What else as a destruction? Absorption. So if this isotope has absorption cross section, definitely it will be gone once you absorb this guy. So what's sigma fission? This is the average sigma fission, is just n multiplied by sigma fission small, and this is n for the fuel. And usually during the reactor lifetime, sigma fission phi, the total number of fission, if you are running on a constant power or something like this, if your reactor is constant power, this will be constant during core lifetime, reactor core lifetime. Again, if you are running on a constant power or so. So we can define a new lambda here, and we call it lambda prime. and I will define it as lambda plus sigma absorption multiplied by phi. So this term is what? Yeah, so sigma fission phi is the term that's constant. And this is just the absorption cross section multiplied by the flux. So you can rewrite this as gamma FB multiplied by sigma fission phi minus lambda prime multiplied by n. Now, how to solve this equation? So dN by dt equals to gamma FB multiplied by sigma fission phi minus lambda prime multiplied by n. So I can rewrite this equation as dN by dt plus lambda prime multiplied by n equal to gamma FB sigma F multiplied by phi. How we will solve this equation? Do you remember the integrating factor?
Yeah.
So this is dy by dx plus p of x multiplied by y equal to q of x. Okay? And the integrating factor will be e to the power of b of x dx. So what's the integrating factor here? E to the power of lambda prime. X here is t, so it will be e to the power of lambda prime delta t, but lambda prime is constant because this is constant, this is constant, this is constant. So lambda prime is constant. You will take it outside the integration and you will integrate dt. It will give you the time. Then if you multiply this equation by e to the power of lambda t, this will give you what? E to the power of lambda prime t dN by dt plus lambda prime e to the power of lambda prime t multiplied by n equal to gamma FB sigma fission phi e to the power of lambda prime t. What's this? This is exact differentiation of what? Of n e to the power of lambda prime t. Yes? This is the exact differentiation of n e to the power of lambda prime t equal to sigma fission phi gamma FB e to the power of lambda prime t. Multiply delta t in both sides and set the integration. So you will reach to d n e to the power of lambda prime t equal to gamma fission product sigma fission phi multiplied by e to the power of lambda prime t dt. At t equal to 0, we have n naught initial number multiplied by e to the power of 0 is 1, and at time equal to t we have n e to the power of lambda prime t. So what's the integration of dx? X. So you will have this substitute by the upper minus the lower. So this will give you n e to the power of lambda prime t minus n naught equal to. This term is a constant. So this will give you what? Gamma fission product sigma fission phi multiplied by the integration of e to the power of lambda prime. It will give you lambda prime multiplied by what? E to the power of lambda prime t from 0 to t, which will give you what? Gamma fission product sigma fission phi divided by lambda prime e to the power of lambda prime t minus 1. If you just bring this one the other side, then divide by e to the power of lambda prime t, this will give you n of t equal to n naught e to the power of minus lambda prime t plus gamma fission product sigma fission phi divided by lambda prime e to the power of minus lambda prime t multiplied by e to the power of lambda prime t will give you 1, and e to the power of minus lambda prime t multiplied by 1 would give you e to the power of minus lambda prime t. So this is a well-known formula if you have production and decay. Yes? So if we do not have production for this isotope, we have n of t equal to what? N naught e to the power of minus lambda prime t. What's lambda prime? E to the power of lambda prime t is just e to the power of what? Lambda plus sigma phi, all multiplied by what? By t. So I will have what? I will have a decay because of what? Because of the normal decay, nuclear decay, and another decay because of what? The absorption. But I have a production, so you will have again the three cases that I showed to you last time. Time n of t, you either have something like this, or you have something like this, or you have something like this. To make it more exact, like, so you'll have something like this. You have something like this, or you have something like this. If we start with no fresh core with no fission products, so what's N naught? 0. N naught is what? 0. And for fresh core, N naught equal to 0, and this will be N of t equal just gamma fp multiplied by sigma fission phi divided by lambda prime 1 minus e to the power of minus lambda prime t. So when you grow up with time, what will happen for this? Decays out. Yes? So you will increase until you reach to at t equal to infinity. This will be what? 0, and you will get the initial value here. You will get to the, it's called saturated activity or saturated number density. You will never increase this number density. Okay, guys? Okay? But what if This is the asymptotic value. But what if lambda prime is very small, is very large? Or actually very small. Very small. If lambda prime is very small, I can expand e to the power of minus lambda prime t to be nearly what? 1 minus lambda prime t, and this term will be what? 1 minus lambda t. So 1 cancel with 1, and you will have what? Lambda prime t. And n of t equal to a constant multiplied by t. This is a relation of what? A line. So this is the line. So this linear relation, when lambda prime is what? Small. So this is lambda prime is small. And actually, we will not reach to this case here. We will not see this case here. Just we'll see those two situations. In order to see this situation, you have to have a very sharp and very rapid decay isotope. It's very rapidly decaying, so it will decay as soon as just you produce it, you will decay. So you'll see. Okay? So we'll have those two situations. So what's the half-life for the isotope? T-half prime. It's like the T-half for anything. It's ln 2 over lambda prime. Yes? And what's lambda prime? Lambda plus sigma absorption what? Sigma absorption phi. And again, we just took what? Sigma average phi is what? Is nearly constant. Sigma average phi is nearly constant. If your production is not constant with time, so you cannot take off this term. You cannot take off this term from the equation. So if sigma fission is, this is we took as average. This is why we said we have to take it outside the integration. It's constant. If it's not average, and this is sigma fission, the number of fissile isotope decreases with time. So you have to get to what relation will govern this n multiplied by sigma fission. So n of t will have some relation. So we have to go back and plug it in here and solve the equation. So let's look for an example here, and we'll look for cesium 137. We'll look for cesium 137. Cesium 137 has lambda equal to 30 here. And the reactor core lifetime is between a year to 2 years. So this is what situation do you think? This is the situation that you will have. The decay is what? It's very, very short, very long compared to the lifetime of the core. So you will reach to a saturation here. Okay? Sigma absorption is equal to 0.11 barn, which is very small absorption also. Actually, I'm sorry. We will be in this situation because lambda is very large. Lambda is very large. Is it lambda? Oh, this is the half-life. So lambda is very short, very small. So we will keep up building cesium during the 1-2 years. We will never reach to saturation activity. During the core lifetime, we will never reach to saturation activity. What does mean saturation activity? Means that you have two competing phenomena going on. One is production, the other one is what? Is decay. So here, there is nothing prevents you, decay does not prevent you from building up. So you are building up, building up, building up. You did not decay anything, so you are increasing. But for this one, you are increasing, but at the same time, absorption will take part of the, some part of your nuclei, decay will take part of your nuclei, so you will have this situation. If your decay and absorption is very fast compared to the production, you will have this situation that I just talked to you about. Did you understand the physics? So, this is just the cesium. If you look for the case for xenon, for example, 135 that we'll study in more detail, lambda, or T, actually T, half is 9.9 hour. And your sigma absorption is 2.7 10 to the power of 6 barn. So lambda prime is what? Lambda prime is just lambda plus what? Plus sigma multiplied by the flux. So this is what? Very small number, because what's lambda? What's 9 hours? Make it in seconds. So 9 multiplied by 60. 9 hours, 60 seconds, 60 minutes, 360, 3,600. Let's assume that this is 10, so you will have 36,000. So this is 3.6 10 to the power of 4. 3.6 10 to the power of 4. Yes? Divided by this. So this will be one third, which is 0.3. It will take one of those. So you will have something like 1 10 to the power of minus 3 for lambda. And what about sigma phi? The flux, let's say, in our reactor is 10 to the power of 13. Okay, per centimeter square per second. Yes, and sigma here is 2.7 10 to the power of 6, but you have to multiply by 10 to the power of minus 24 to transform it from barn to centimeter square. Yes, so this is what? 20, and this is 20 10 to the power of minus 4. Yes. So lambda is 10 to the power of minus 4, 4-ish. This is 10 to the power of minus 3, this is 10 to the power of minus 4, so it will be 10 to the power of minus 4. 10 to the power of minus 4 is what? Very short. Yes? So you can expand it, you can expand the, you can look for this situation. You will look at the cesium build up. So during your reactor operation, if you want to look at time during the reactor operation, and this is N of T, and we'll look at cesium, so you look at cesium like this. cesium concentration as a function of time. And you will look for the xenon. Xenon will be like this. You will grow up, then you will reach to saturation very rapidly. You will reach to saturation. So this is just an example of how to calculate the reactivity from reactivity inventory inside the nuclear reactor. So if, for example, when we do the reactor design, we do the core analysis, we do everything. There is some codes that calculate the reactivity inventory inside your reactor, and I think the code is called Origin. I think it's for radiological consequences. You want to see how the radioactive material will build up. So all those equations you will solve, and there is chains of radioactive chains, and there is equations called Batman equation. You have to solve those Batman equations, and you will have inventory calculations. So one of the well-known codes is written by a professor in University of Wisconsin-Madison and Fusion Technology Institute. It's called ALARA. It's not the ALARA. It's not the as low as reasonably achievable concept for the radiation protection. This is called adaptive Laplacian blah blah blah, and his name is Paul Wilson. So if you are interested, you can look at his code and program online at the Fusion Technology Institute. This is at Wisconsin, wisconsin.edu. So it solves those equations, and it gives you the activation and so on. So now, we just looked at a general formula for a decay and absorption and a production for a radioactive isotope. Let's look for the second case, which is the buildup of xenon and samarium, which is they are considered as poisons in the nuclear reactor. Why they are considered poisons? Xenon and why they are considered poisons? Because if you digest them, you will die. Can you go and drink some water in the reactor and then take some piece of samarium and chew it and see if you will be alive, or if there is something alive? I'm sorry guys for the so is it considered poisonous because of this? Because of what?
It lowers the reactivity of the reactor.
Yes, so they will introduce a high absorber inside your reactor, and this will affect greatly the F multiplication factor through F, 1 over the sigma absorption and the fuel divided by sigma absorption everywhere. So you increase the sigma absorption everywhere. Okay guys, so let's look at the samarium and xenon. So xenon, it's 135, samarium is 149. The lambda is very large, very large. So the decay constant is very large and very short half-life, and sigma absorption is very large, and this is what we saw just in a minute. So let's look at the case for xenon. 135. So you have T half, just wrote it, 9.9 hour. Sigma absorption is 2.7, 10 to the power of 6 bar. Flux here is 10 to the power of 14 neutron per centimeter square per second. Lambda prime will be just lambda plus sigma absorption phi, and this will give us 2.91 10 to the power of minus 4 second minus 1. So the effective half-life is just equal to T half prime 0.693 divided by lambda prime, and this will give you nearly 2380 seconds. So very large half-life. Yes, very extremely large half-life based on the absorption and the decay. What makes this, so the decay half-life is just 10 hours, but what makes the effective half-life very large is what? The sigma absorption phi term. Because sigma absorption phi term is very, very small compared to the 9.9 hours. So it will be, because of this effective half-life, it will be less than an hour to reach saturation activity. And then if we look at the samarium, the samarium 149, the samarium does not decay. So the samarium does not decay. And the absorption cross-section for samarium is just 41,000 barn. Lambda prime will be 4.1 10 to the power of 4 multiplied by 10 to the power of minus 24. This to give it to you 4.1 10 to the power of minus 20 in centimeter square. This is what? No, I'm sorry. And this will be, if you multiply sigma phi, we have to multiply by the flux. But anyway, the T half prime will be nearly 6 hours. We'll study those in details right now. So let's look at the xenon. So the xenon is produced directly from fission. Produced directly from fission. What does it mean? It means that I will have gamma xenon. Yes? And gamma xenon is just very minute fraction, 0.00237 for uranium-235. And again, it produced from the decay of iodine, 135. So this will be xenon, will give you 135. So you have tellurium, 135 will decay, give you iodine, 135 will decay, will give you xenon, 135. So the tellurium is produced in the fission. This also produced in the fission. This guy decay through beta decay in 11 seconds, and this guy decay in 6.7 hours through beta decay, gives you xenon 135. It decays through beta decay, give you cesium 135. Decay through beta decay gives you barium 135, which is a stable isotope. So we will look here. This is just 11 seconds, and this is 6.7 hours. So you will assume that xenon mostly come from what? From iodine. Why? Tellurium is just stay there for 11 seconds, 20 seconds, 1 minute, all the tellurium will be gone. So now we want to write the equations for the xenon production. Those equations will be a little bit different from the equation that we just stated. Why? Because the production, when we study the equation for the fission products, it was just the production coming from what? Fission, and minus absorption minus decay. Yes? Now the production is coming from fission, which is a constant rate, but plus some other part which is coming from what? Iodine, but I do not know the iodine, so I have also to include the equation for the iodine. So I will have two equations, one for iodine and one for what? Xenon, and I will have a system of linear differential equation of the first order to solve. So I will have the first equation for the iodine. Let me write the equations here. I will have di of t for the iodine by dt equal to iodine is generated from fission with gamma I sigma fission phi. It decays through lambda I iodine. So iodine here, I capital is what? What's I capital? It's the concentration of I. So instead of writing N, I wrote I, so that we will have a differentiation between N iodine and N what? Xenon. N xenon, I will write it as X, Xe, or X. So the second equation is d by dt for X, and this is equal to, what's the first term? Where also you produce this, you produce xenon from the decay of what? Iodine. So all the decayed concentration of, or decayed activity of iodine will show up as what? As xenon. So this guy, once it decay, you have one curie, which is what? 3.7 10 to the power of 10 becquerel or disintegration per second. So this 3.7 10 to the power of 10 disintegration per second of iodine will be transformed to what? Xenon. So you are producing xenon at the rate of 3.7 10 to the power of 10 nuclei per second, minus the decay of xenon, minus sigma absorption for xenon multiplied by 5. So I will stop here because I have to do lots of work in order to reach to the final solution. So I would love to stay here and then come next time to solve those two equations. Do you have any question so far? Anything? Everybody's happy? Prepared for the last exam, final? So give you the final tomorrow instead?
No. Is that going to be